Unified quantum classical computers. Why should we talk about this? Well, for long, physicists have been obsessed with unifying quantum and classical things, like the fundamental theories of nature. But this is a really hard problem. We don't know how to solve it, at least I don't know how to solve it, so today we're going to stick with unifying computers. And if this is not an inspiring enough explanation for why we should talk about this subject, then how about we start by asking, why are we all here? And I don't mean why quantum mechanics and general relativity conspired together to bring us all to existence. I mean, why are we all here in this room today? What are we all after? What is our common goal? And I think all of us are here today, this entire community really share a single common goal, and that is to bring quantum computers to practicality, bring practical quantum computers into reality. I think that all of us are here today because every one of us really believe at the end of the day that we can do this, we can make this happen. And I also think, I hope that all of us here today also understand that we have a long road ahead in order to make this happen. So in order to reach a point in which quantum computers solve practical problems, real-world practical problems, we have a long road ahead. So how can we move faster along this road? Well, one of the more important answers that we've been discussing and that became clearer and clearer in recent years is that in order to reach quantum practicality, it's required to integrate classical and quantum computing in a very intimate way, tightly integrate quantum and classical computing. I really see it as kind of like a turbo engine that sort of makes us drive faster along this road. So, or kind of like the nitros that Vin Diesel is using to win every race. I thought that Vin Diesel is a universal phenomena, just like quantum mechanics, so it deserves a spot on the slideshow. But let's break it down a bit further. So, actually, there are two main reasons, two important reasons why we want to integrate quantum and classical processing. First, we really want to squeeze the performance out of the QPU. So the quantum hardware is not where we fantasize it to be today, unfortunately. But it turns out that by integrating deeply with quantum computing, with classical computing, we can really improve the performance of our quantum processors. And the second reason is that we really want to, if you really want to solve a practical, real-world problem, you need to run hybrid workflows. So think about a factory where you have many people and many machines, and each machine is doing a different thing. So the QPU is only good at certain tasks. Or think about a company where you have many people from many disciplines trying to achieve together a single goal. You wouldn't want your quantum physicist in your quantum startup to do finance work because you'll be bankrupt by the end of the quarter. So you don't want, in the same manner, your QPU multiplying numbers or doing things that you can do in your classical processor. So I want to kind of give you a little bit of more concrete examples, a few concrete examples to sort of get the feeling of why this is important. So the first example that I want to give is the calibrations. This is a good example of how we integrate quantum and classical processing. Because when we calibrate a quantum computer, what we typically do is we send a bunch of pulses with different shapes and different parameters to the QPU, and then we take some quantum measurements of the QPU, and then we need to process to analyze these quantum measurements on the classical processor in order to find what are the parameters that will optimize our quantum operations. And actually, the tighter the quantum classical integration, the faster and more frequent can we run these calibrations, so we can actually reach better fidelities and also higher uptimes of our quantum machines. Another good example is quantum error correction. In quantum error correction, we need to do what's called mid-circuit measurements. That means we take measurements of some qubits while the quantum circuit is running. And again, we need to analyze those, process them on a classical computer, and to sort of discover what are the errors that are occurring on the quantum processor and fix them in real time. And that's, again, very integrated quantum classical processing right there. And of course, there are variational algorithms that heavily rely on classical processing in order to optimize the cost function of interest over the parameters of a quantum circuit. So we send a quantum circuit to the QPU, we make some measurements, again, we analyze these measurements on the classical side, and then we need to update the parameters of the quantum circuit to minimize the cost function of interest. So in all of these examples, you see that quantum and classical processing are sort of interleaved with one another for various reasons and in various ways. And there are actually many more examples. So quantum error correction, I mentioned, active state preparation, dynamic circuits is a big one today, optimal control for pulse optimization, embedded calibrations, variational algorithms, there are many more. And really, we want to combine all of this together when we want to run applications in order to get the best performance, the best results. So if you want to run a QAOA, for example, you might want to also do active state preparation and do optimal control and add dynamic decoupling. And so we need to start creating these very complex workflows that are actually at various levels in the stack and combine them together into a single workflow that then needs to run. And the key is that it needs to run very efficiently on the underlying hardware and software. And that's why we need to build a unified quantum classical system, an integrated quantum classical machine. And we need to carefully design it. So what are some of the considerations that we need to have when we're building these unified quantum classical machines? So we took all of these use cases and we started categorizing them according to two different axes. First is the timing axis that you see there on the bottom. And then there is the vertical axis, which is categorizing according to functional requirements from these quantum classical processing. So on the bottom, you see we have real-time quantum classical processing and near real-time quantum classical processing. So real-time quantum classical processing is where we want the quantum classical interaction to have a very, very extremely low latencies that are actually shorter than the coherence time of our qubits. And typically, this also needs to be deterministic latency. So very ultra-low latency, deterministic latency. This typically also means that we need to run the classical processing very close to the QPU, typically in the quantum control hardware, which I'll talk about in a second. And then we have the near real-time quantum classical processing that, of course, we also want to have the quantum classical latency as short as possible, but this is less constrained by the quantum system itself. And also, we many times want to use heavier classical resources like cloud and HPC. So this is sort of the map of the world. And then I didn't talk about the vertical axis so much, but this is, again, I won't go into too much details on this one, but this is the functional requirements. What do we want from this quantum classical interaction? So for example, performing conditional quantum operations that are conditioned on the results of classical processing, or doing full control flow of the quantum classical program, kind of like what Joe discussed just a few minutes ago, and then also doing updates of parameters of the quantum operations based on classical processing, which is based on the quantum measurement. So all sorts of different functionalities that you need to have. So this is the map of the world. And so in the rest of the talk, what I want to do is I want to tell you a little bit about what we at Quantum Machines are doing in order to take those considerations into account and build a quantum classical machine. So I'll start from the real-time part, because this is what Quantum Machines has been pushing very strongly in the last several years. This is our core technology, and then move to talk about the integration with heavier quantum classical processing, which is what we're pushing very strongly these days. Okay, so QM. So at QM, we're focused completely on the quantum control stack, quantum control hardware and software. Our goal is to bring out the best out of any quantum processor or device out there, and to achieve fastest time to results in quantum computing. So a quantum computer, at the heart of the quantum computer is really built out of two components. We have the QPU, okay, that's what we all know. That's where qubits are. That's where we have the quantum magic, the entanglement, the interference, all the stuff, good stuff. But then we also have the control and orchestration platform. So this is classical hardware and software that's responsible to generate all the signals that actually drive the QPU and make it do what we want it to do, and also measure signals coming back from the QPU. This is what we're doing at Quantum Machines. We're focused on the control and orchestration layer of the quantum computer. At our core technology, we've developed a new type of processor, not a quantum processor, a classical processor. We call it the pulse processor. And this is the processor that's responsible to orchestrate the quantum program, if you want, on the most kind of physical level. It orchestrates all the pulses and measurements that happen in the control and orchestration system. And we were the first to really integrate classical processing into the pulse processing unit itself in the most general sense. So the pulse processing unit integrates the quantum operations with the classical operations, and they actually run from the same chip. And we've built a programming language that we call QA that allows you to write these real-time quantum classical programs. Recently, we're also doing a lot of work in integrating with the standards that are forming in the community, like OpenQASM 3, that are actually going in the same direction of integrating classical processing deeper and deeper into the quantum computing stack. So I just want to give you a little bit of a feeling of how QA looks like, just not to go into the details, but really sort of to understand how we can tie together quantum and classical processing in the most intimate manner to run together in the same code. So QA has quantum operations at the pulse level, so we can play pulses to qubits and we can measure signals coming from our qubits. But we also have general classical processing, like in any other quantum language. But this runs on the control hardware, the quantum control hardware. Okay, so you can say A equals B squared plus 5, just like you do in Python. But then you can also tie them together. So you can send a pulse to a qubit and change the shapes of these pulses based on these classical variables. And in the same manner, you can feed the classical variables from the quantum measurement. So I can measure my qubit and save the result into a classical variable. And then I can keep processing, classical processing of these variables. And I could do control flow. I could say, if my qubit is in the excited state, I want to play a pulse to that qubit or the other qubit, or if I'm measuring, while I'm measuring some error syndrome, I'm doing something else, etc., etc. There's, of course, full timing control. So this is the idea. This is how QA and the pulse processor bring together quantum and classical processing. And everything here runs in real time with the absolutely fastest feedback latencies in the industry. All right, so this is how we sort of deal with the real-time parts of our unified quantum classical machine and get the best results possible. But of course, we now also want to integrate with heavier cloud or HPC resources. So we've started looking at that a couple of years ago, and I want to share some of our thoughts and the vision that we've came up with as we went deeper and deeper into this. So today, what we're seeing in the field is that what we call the standalone black box HPC QC model, where you have your classical computer, and then you get a quantum computer, and they're loosely integrated in a sense that I'll mention in a bit. And if you look into the quantum computer, you see sort of like three major components. We have the QPU, of course. We have the control hardware that I just mentioned, but we also have a bunch of software, a lot of software. So this includes the compilation, the optimization, the automation, and other things that are all running in the quantum computer, and there's no real access into them. And then you program your quantum computer via some high-level, typically a gate-level language. You send a task, you get the result back. And there is a problem with this model. There are a few problems. First, there is no access to the critical low-level capabilities that we need in order to, again, squeeze the QPU for performance. For example, the pulse-level features and this real-time quantum classical processing that I mentioned. Second, there is no ability to leverage the HPC to run the control hardware, the control software part, right? The hardware-aware control software, because it sits on the wrong side. And third, there's no ability to run hybrid workflows efficiently. And this is what I meant by loose coupling, is that typically you cannot co-schedule, do joint scheduling of the resources even. So you run something on your quantum or your classical computer, and you need to wait for the quantum computer and vice versa. There's also hardware integration considerations, including latency and more. So we want to change the paradigm. We want to first move the software to where it belongs, to the HPC side, so that users also can access it and can leverage the HPC to run it. Of course, we want to provide our control systems, because it's the best control system that exists out there, with the pulse processor and with QA. And this is already, you can already see that this is a unified system, right? You cannot say where the quantum computer is anymore, right? A lot of the quantum computer sits actually on the classical compute side, right? So it's a unified machine. And we're not losing anything, because we can still do all the high-level stuff. We have the high-level libraries, high-level gate level and above programming models that we can compile down to the low level, but on the classical side. And we get the low-level access to what we call now the quantum node. It's no longer a quantum computer. We have a GPU node, a CPU node, and a quantum node. And so this is the machine we kind of imagine. On one hand, it solves this real-time, deterministic, low-level, low-latency quantum classical processing due to sophisticated control and with all the use cases. And it allows us to bring this near real-time requirements also with the integration with the HPC. And that's kind of the vision that we're pushing. We have several projects going on right now where we're striving to do exactly this. So I'm not going to put Van Diesel's pictures again, because we're physicists after all. It's too cool for us. But I do want to put this picture on, because beyond performance, which is super important, I think that as we're building these systems, we also need to think about productivity. Developer experience and productivity are extremely important, even if you program at the very low level, because only by that, this is the only way that we can really accelerate this build, measure, learn cycle and achieve quantum practicality at the end of the day, which is why we're all here. So with that, I hope that I managed to convince you that we can accelerate the realization of practical quantum computers with integrating quantum and classical computing. This is what we're all about at Quantum Machines. So if you're interested in that, please come talk to us. We believe that we can push this by providing the technology that makes it seamless to do so. And with that, let me thank you, and I'll be happy to take any questions. Yes.
So you have one quantum processor and one classical processor. In the future, a quantum computer may have 50 quantum processors, so to speak. So are you guys looking far into the future about how to integrate communicating between quantum processors?
Yes, definitely. So the control system, so there are a lot of things to say about it. First, even for large QPU, you can kind of slice them and use them in sort of chunks of the different QPU, and this is some of the features that we have in our control system actually allows you to do so. Is actually being utilized a lot when you calibrate a machine, right? Because you don't want to calibrate that qubit and all the rest are doing nothing. So you actually want to calibrate in parallel. So another application of this would be to really cut the QPU sort of to pieces and do like virtual quantum processors. And that's one of the features that we have. Another thing is, yes, I think that it's interesting, when you look at these variational algorithms, that actually when you think about it, many of the quantum applications that we have are sort of highly distributable, right? Because we need to take many shots of the same circuits millions of times. And so we could gain some by having multiple QPUs. And then you have also, of course, building a large QPU by having many QPUs that actually communicate with quantum quantum networking. So all of this is extremely important, and all of this also has implications on the control system, because to start communicating between chips, even though the communication is quantum, there are implications on how you need to build a control system, and that's very important. And you can squeeze more out of your QPU. Again, your integrated now QPU from 2 QPUs if you have sophisticated control that includes these feedback, feed-forward mechanisms that we support. Yes?
So a question about the classical computation embedded in the circuit. So with that capability, what have you found to be the impact on how that would change your algorithms? Does that make new kinds of algorithms possible? What are your thoughts?
Yeah, so a good example, I think, are dynamic circuits, for example. So in many cases, it's not going to change the application that you're trying to run, but it's going to change how you run it, and maybe help, as I said, squeezing the QPU. So, for example, it could lower the circuit depth because you have now these capabilities to do mid-circuit measurement and based on them perform your quantum operations. That's one very important thing that I think is going to be, or when you prepare magic states, for example, in quantum error correction, you do repeatedly success operations. So all of these classical processing that are embedded really into the control layer now are very important in order to do these kind of things, to run same applications, but with much less gates, essentially. And the other thing is, it opens up the way to things like running the calibrations really from the hardware itself, so that you can make sure that your QPU is always tuned to the best fidelity. So I think it's more about this than new applications, but maybe that as well. Okay, here I think.
Being the token ex-Red Hatter here, now working at Quantum Brilliance, I'm very curious, you mentioned the importance of developer experience and the onboarding. What are you finding that's working in your experience so far, or that you're seeing as a best scenario in the industry that the rest of us could be learning from or adapting?
So the question is, like, what do I think is important in that respect?
Yeah, specifically examples of developer experience, given that it's a hybrid model, that might be bringing the next wave of developers in.
So first of all, so I won't comment too much on everything that's happening in the industry. I think there are many important tools that allow you today to write hybrid workflows. One of the things that we're doing, actually, so we're interested in all these calibration workflows and things that are kind of happening at the low level. One of the tools that we've developed internally to solve some of our issues was a workflow tool that allows you to write complicated and highly distributed and decentralized workflows where different processes run on different resources and can communicate with one another in sort of message passing methods. And that, for us, was extremely important for productivity. Because one of the main things that I think are difficult with quantum computers versus everything that we have for classical computers is that when you work with a quantum computer, you have to work very interactively. Because it doesn't work that well yet, right? So it's kind of like an experiment, like a physics experiment, right? You're running something on your QPU, you want to see the data, you want to change the circuit you're running, and you really want to work interactively. And then you want to start automating that and running these hybrid workflows in an automated manner. So all of this juggling between interactive mode and automated mode, I think that's one of the major things that needs to be solved. We did it internally with this tool that we call Entropy Flame, and we're now putting it out there as an open source tool for the community, so I hope that people will use it. But I think that kind of things are going to be important as we move on. Yeah.